In our laboratories today, we live in an atmosphere dim with the flying fragments of exploding atoms. And to realize, if even on a small scale, the old dream of the alchemist of transmutation of one element into another. I've witnessed an astonishing increase of our knowledge. At the close of the 19th century, and the atoms of these elements appeared to be permanent and indestructible by the forces then at our command. That radioactivity was a sign and measure of the instability of atoms.
This is a workplace, a laboratory run by Cambridge University. The people here are scientists, and their job is to make experiments work, to find new knowledge and to make discoveries. And this programme's about discovery. What is it? And how do these people do their jobs? Is getting the right answer to some scientific problem a matter of patient hard work, methodically working through experiment after experiment? What part does pure genius play? And sometimes, just sometimes, does luck or chance play a part? Now, Democritus, he was an ancient Greek, a philosopher, asked, if you had something, now I've got this piece of paper, and you tear it in half again, and again, and again, can you go on tearing forever? Okay, at some point my fingers will get too big to hold the paper, but in theory, was it possible to go on cutting forever? Now, Democritus imagined, and remember that he just imagined, there was a point beyond which you couldn't tear anymore. Now, he didn't do any experiments. He just imagined that there was a stopping point.
In his mind's eye, Democritus imagined a very, very tiny, very, very hard sphere, which was impossible to split. This hard, tiny sphere is the atom.
Democritus had made a model of the atom, tiny, hard, round and solid, rather like a billiard ball, really. Now, for 2,000 years after Democritus, thinkers, if they ever needed to think about atoms at all, imagined them like this. But in the 1890s, something happened to change this idea. Now, this thing here is called a Crookes tube. Inside there's a gas at very low pressure. In fact, it's almost a vacuum in there. Now, a very high voltage is passed between these two terminals. Watch what happens when I turn the power on.
In the 1890s, no one knew exactly what these rays were. This man, John Joseph Thomson, J.J. Thomson, was trying to find out. He found that the rays weren't rays, that is, they weren't some sort of light, rather that they were streams of particles, lumps of solid matter.
Thomson was able to work out their weight, and they were much, much lighter than any estimate of the weight of atoms. He did experiments on the particles using magnets and electric fields. These showed that the particles were negatively electrically charged. Now, no matter what gas was in the Crookes tube, the particles behaved the same. They were present in all substances. Thomson called the particles electrons.
What did his discovery mean for the billiard ball model of the atom? Obviously, there was something much, much smaller than any known atom. And since the gas that was in the tube was electrically neutral, but the electrons were charged, it seemed that the smaller particles were parts of the gas atoms ripped away by the voltage. A new model of the atom was needed. Thomson imagined one. His model was still a solid ball, mostly electrically positive, but stuck on the surface were the negative electrons.
Well, this model was thought to look like a plum pudding, the unseeable described in terms of something which could be seen, and this was the name that stuck. At the same time as Thomson was experimenting with his tube, other scientists were approaching the atom by very different ways. Wilhelm Röntgen, one of the luckiest of scientists, is remembered as the discoverer of X-rays. He was messing about with the Crookes tube, And on his desk nearby was a screen of card covered with barium. And when the tube was turned on, the screen glowed. Now Röntgen worked out that the glow was caused by invisible rays from the tube. He hadn't a clue what they were or what caused them. X stands for the unknown. Now they had mysterious properties. Whilst they were similar to light, they could also shine through solid objects.
A Frenchman, Henri Becquerel, heard of Röntgen's luck and it made him think. Unlike Röntgen, Becquerel knew what he was looking for. Becquerel was an expert on luminescence. Some substances glowed by themselves naturally, and he wondered, were there substances which gave out the invisible X-rays naturally?
He found what he was looking for. This stuff will mark a photographic film in the dark. Potassium uranyl sulfate, a combination of potassium, sulfur and uranium. Becquerel worked out that of the three, it was the uranium which gave out the rays. Becquerel had a student, a brilliant young Polish woman married to an equally brilliant young Frenchman, Pierre and Marie Curie. Now, gave them the job of sorting out what was odd about uranium. They found something strange. This is pitchblende, the crude rock from which pure uranium metal is refined. Now, common sense might make you think that the pure metal will be more radioactive than the crude rock. But it was the other way round. Radioactive, by the way, is just a word invented by the Curies to describe giving out of rays. Now, the Curies wondered if there was another radioactive element more radioactive than the uranium in the pitchblende, and they set out to find it.
Pierre and Marie were chemists and they used chemistry to test their guess. They had a huge pile of pitchblende. They boiled, filtered, distilled, all with crude kit in an old garden shed.
After 2 years, they got from 1 ton of pitchblende 2 new elements, polonium and radium. And from their ton, they only got about 1 gram of radium, tiny amount, but so radioactive it glows of its own. Now, the achievements of the Curies were very great. To describe radioactivity, to discover 2 new substances with such incredible properties was enough to make them famous. More important than all that, they gave other scientists powerful tools with which to work.
Quickly it was found that there were 3 types of radiation coming from the new elements. This experiment showed them. Alpha radiation. This was found to be large particles positively charged electrically. Beta radiation. This too was of particles, but tiny, much tinier than alphas, and negatively charged. They were found to be identical to electrons. And there were gamma rays, not particles, not charged, pure rays like X-rays, invisible and penetrating.
Knowledge of these radiations and the existence of the powerful sources, polonium and radium, were the next steps in discovering the atom.
Ernest Rutherford. In 1908, he was Professor of Physics here at the University of Manchester. Rutherford wanted to know how the atom was made. Was it really like a plum pudding?
The atom was so small it couldn't be seen, but Rutherford thought of a way of feeling the atom. Now, over there is darkness, it's the unknown, and I don't know whether there's anything in that darkness or not. If I take a ball and throw it, and it goes straight through, I know there's at least some empty space there. If I take another one, and it comes back, I know that there is something in there. And if I throw enough balls, and I look at how many go straight through, and at what angle they come back, I can begin to make a good guess as to what the shape of the something inside is.
And it was here at Manchester that Rutherford threw alpha particles to feel the atom.
It was in a room near here in 1908 that he carried out one of the most important scientific experiments ever. Now, to explain it, we've built this model. Now, in here is a source of alpha particles, and Rutherford actually used polonium, which was given to him by Marie Curie. Now, the alphas shot in a beam towards this target made of very thin gold foil. And this bit here is a microscope, and on the inside end is a screen made of zinc sulfide, which actually gives out a flash when it's hit by an alpha. So by counting the flashes, Rutherford could count the alphas coming from the polonium. This is what you could see through the eyepiece.
Over 90% of the alphas came straight through, but some, about 1 in 8,000 to be a bit more accurate, went everywhere, or rather anywhere, or even straight back. The microscope could turn round so that Rutherford could look for alphas at any angle. So what does this mean?
Well, one, since most alphas went straight through the foil, most of gold atoms must be empty space. Two, alphas are positively charged. Now, positives are repelled by positives. Now, those alphas that bounced away must have been hitting something, and that something must have positive charge. Now, some things must be very, very tiny, since so many alphas came through the foil.
If atoms were Thomson's plum puddings, they'd be solid and have no electrical charge. Rutherford had found empty space and charge. The plum pudding was a model which no longer fitted the facts, and Rutherford created a new model. A sphere of fast-moving electrons orbiting around a central but very tiny positively charged nucleus.
So much for puddings, hey? In science, there are those people who are great thinkers, who can take away a problem and come up with an answer just by power of imagination. There are also the great experimenters, sort of scientifically green-fingered, I suppose, and they see how to turn a problem into real lumps of metal and glass on a lab bench, and the equipment just works for them. They're the sort of people from whom in school science lessons you copy the results. Rutherford was one of those clever types. Since the atom was now thought to be planetary, the next question was obvious. What was the nucleus like? Well, Rutherford again experimented using alpha particles to feel the atom, and this is a model of the equipment he used. A piece of polonium and a microscope with a screen to detect flashes. And through pipes here, Rutherford could put various gases. What was Rutherford trying to do? He thought this: if an alpha particle hit a smaller, lighter particle, then the lighter particle would travel faster and further than the original alpha. It's only common sense, really. Now, it was known that alpha particles were heavier than the nuclei of hydrogen, and the nuclei of hydrogen made a different sort of flash on a zinc sulfide screen. Rutherford reasoned that since hydrogen was the lightest element, it would have the simplest atomic structure. Again, common sense. And he thought, and well, it was only a guess really, that hydrogen nuclei might be the building blocks from which all nuclei are formed. A proof of this idea would be to knock a hydrogen nucleus out of the atoms of another element.
In 1919, Rutherford filled the tube with nitrogen and shot alphas into the gas. It worked. Hydrogen nuclei were found at the other end. His guess was right.
Well, it's been easy for me to talk about Rutherford's experiment. I've made it all sound dead easy. But it actually took Rutherford years to be happy he'd found the right answer. For a start, there had to be no grease or dirt inside the tube. This would have given the right result, but not a true result. And he had to make sure there was not even the slightest trace of hydrogen mixed in with the nitrogen. For the result to be true, Rutherford had to find hydrogen where he was sure there had been none before. The hydrogen nuclei knocked out of the nitrogen were positive charged with atomic weight 1. They were given a special name, protons, and were found inside the nuclei of atoms of all elements.
Rutherford went on to work out a neat fit between the number of protons in the nucleus and the atomic number of any element. Hydrogen, number 1, had 1 proton in its nucleus. Nitrogen, number 7, was found to have 7 protons. Oxygen, number 8, was found to have 8 protons. This fit was beautifully neat. One big problem though. Whilst the number of protons matched the atomic number, it did not match the atomic weights. Now then, hydrogen, 1 proton, atomic number 1, atomic weight 1. Nitrogen, 7 protons, atomic number 7, but atomic weight 14. Twice as much as it should be. Take oxygen, 8 protons, atomic number 8, that is 8 times more protons than hydrogen, but atomic weight 16, that is 16 times heavier than hydrogen.
Rutherford thought hard about this problem. The fit between protons and atomic number was too neat not to be correct. It had to be right. But what about the problem with atomic weight? In 1920, Rutherford gave a lecture in which he talked about this problem.
He thought the answer was that in the nucleus, and this one's nitrogen, there were the protons, so there were 7, and an equal number of another type of particle of equal weight to the proton. This would make nitrogen's weight of 14. But these second particles were neutrally charged, neither positive nor negative, and they'd never been detected. Rutherford gave this particle a name, the neutron. Just remember this. What Rutherford had done was to make another guess as to what the answer might be. His just saying there could be a particle, the neutron, didn't make it so.
The neutron had to be found. To find the particle which would make sense of the atom was not easy. The problem was that of finding a particle which carried no electrical charge.
Rutherford liked to find particles using the zinc sulfide screen and microscope. This method only worked for charged particles. All other methods known to Rutherford, the Wilson cloud chamber, the Geiger counter, the Wolf-electroscope, none of these could detect neutrons because all of them worked only with charged particles. At the same time as he made the prediction that the neutron would be found, Rutherford guessed how the problem might be overcome. He likened the neutron to the Invisible Man. He said,
"How could you find the Invisible Man in Piccadilly Circus? You couldn't see him, but you know he was there by the people he collided with, by the reactions of those he pushed aside. Recoil, my boy. That's how the neutral particle gives itself away."
This is what Rutherford meant. Here's a charged particle. Imagine it's a proton. Now here comes an invisible neutron. Now Rutherford thought of the experiment which would find the neutron in 1920, but it was 12 whole years, before anybody actually built the experiment so it worked. Now Rutherford began the search for the neutron at about the same time as he started a new job. He left Manchester to become Professor of Physics at Cambridge University. Rutherford's job here was not simply to do experiments. He was by now a very big and important scientific boss. He was head of this laboratory, the Cavendish.
He was head of a large team of scientific workers. It contained some of the best physicists in the world. This team was set by Rutherford to find the neutron, to solve the problem of how the nucleus was made. The main worker in the search for the neutron was James Chadwick.
It was to take 12 whole years. Now, throughout the 1920s, Rutherford and Chadwick tried to find proof of the neutron. They and the researchers who worked for them tried many different ways.
I made a number of experiments on both these lines, some of them wild gambles, which might now seem worse than wild, even stupid. And I made some which could have given the answer I was looking for.
But workers such as John Roberts put things a bit differently.
I wasted a lot of time on some crazy idea of a prof or Chadwick's.
I did a lot of experiments about which I never said anything. Some of them were really quite stupid, I suppose. I got the impulse or habit or whatever from Rutherford. he would do some damn silly experiments. There was always the possibility of something turning up. Until 1932, you see, it was in many ways a frustrating time. I didn't see any other way of building nuclei, so I did quite a number of silly experiments. I must say, though, the silliest were done by Rutherford.
Scientists spend a lot of their time calling other scientists' work useless. 1932, 12 years from Rutherford's guess. In all of this time, Rutherford, Chadwick and their team were patiently trying this and that, eliminating the different ways of finding the neutrons. All they had was faith that the particle must exist. They couldn't build an experiment to prove it.
But the more general reason was a lack of technique, for the methods of detection of individual particles had not then been sufficiently developed.
So what gave the final answer? Again, luck played a part.
This is Irène Joliot-Curie, daughter of Marie, with her husband Frédéric, both scientists working in Paris. In 1932, they performed this experiment. An alpha particle source in a brass tube. The alphas are hitting this sheet of beryllium. At this end, a counter. It'll find any charged particles, and a photographic plate. It'll detect any rays X or gamma. They found two things. First, very strong rays, X-rays. Second, positive charged particles, protons. Irène and Frédéric put different types of screen here to filter out the particles and rays to get some measure of how strong they were by seeing what would stop them. And then something weird happened. They used a sheet of paraffin wax. The number of protons doubled.
Now clearly something very strange was happening. Putting a barrier in front of the radiation, doubling it goes against common sense.
Irène and Frédéric's instant reaction was to doubt their results. They checked the equipment, they did the experiment again, they checked the calculations, they got the same results. They claimed a new, totally unexpected discovery, and remember that, it was unexpected. They claimed to have found that X-rays could knock protons out of nuclei.
A completely new idea, and one which was completely wrong. Very quickly, mathematicians, pure thinkers, showed that the X-rays simply were nowhere near powerful enough to do what Irène and Frédéric claimed, a mystery.
But not to Chadwick. He did Irène and Frédéric's experiment again. He reasoned, what if an uncharged particle, invisible to the Geiger counter, of about the same weight as a proton, was hitting the atoms of paraffin wax? Would this be strong enough to knock protons out?
Recoil, my boy. That's how the neutral particle gives itself away.
Chadwick had found the neutron. Neutrons were coming from the beryllium and hitting the protons from the paraffin.
This is the real piece of equipment he used. Now, finding the neutron completed the picture of what the atom was like and won James Chadwick the Nobel Prize for Physics. Irène and Frédéric could have won that prize.
Were they bad scientists? Incompetent? Hardly. Irène went on to win 3 Nobel Prizes. Irène was to tell Chadwick that had she known of Rutherford's 1920 prediction, she would have seen straight away what was going on. Irène and Frédéric didn't find the neutron because they didn't expect to find it.
It had taken 12 years to make that discovery. Progress in knowledge of the atom had virtually stopped. But with the discovery of the neutron, nuclear physics began that rapid progress in both science and technology, which has continued to this day. Well, we began this programme in a scientific laboratory, and this is where it ends. OK then, scientific discovery. What is it? Well, it can be very difficult. It can involve a lot of patient, hard work. And sometimes luck can be the turning point. And sometimes discovering new knowledge can be just a question of seeing exactly the same facts as everybody else, but seeing them differently. Sometimes discovery is a matter of proving right a good guess, or to put it another way, proving wrong somebody else's ideas. But if you do that, you have to come up with something better. So when you do science, think about it.